My name is Mata. I obviously work for Kinetica. I'm a software engineer there, but I also do a lot of work in the field for customers. So basically our agenda today is to talk about GPU databases, especially in the context of hosting varied applications, particularly AI and ML and deep learning. So we'll talk about GPUs themselves, AI, and why ultimately apps are smarter on a platform that can facilitate all that. So GPUs intuitively at first glance, I know when I heard about them, you think performance. GPUs should, for certain computations, run much faster than CPUs, taking advantage of the number of cores they have. So we're talking on the order of 3,000 cores on a GPU card compared to some factor of 16 cores on a CPU socket. So there are imperatives for using GPUs in a system to facilitate analytics. Ultimately, it's a buzzword, right, saying do more with less. But the fact is, if you follow the imperative of using CPUs, GPUs holistically, you should be able to get more throughput for various categories of computation, leveraging those cores. But again, you have to build from the ground up holistically and know how to schedule, orchestrate all that. So, that leads me into saying, why ultimately have a GPU database? Again, we want to be able, our goal was to have a platform that leverages GPUs, CPUs, that can handle traditional computing as well as the emerging AI genre, real-time ingestion at the same time. SQL databases aren't necessarily built and optimized to real-time ingest and host AI. They're excellent at SQL. I'll go even farther to say that SQL databases, in order to handle big data and fast turnaround on the big data, supporting fast analytics, fast computation, high throughput, have to be in memory. So again, these are the imperatives which we've listed. We want to be able to handle these categories of function on one hardware platform, resulting in a simplified software stack. So, a lot of people ask, what are AI, ML, and deep learning? AI is, in my opinion, any algorithm that does something smart. All right, a rules engine is AI. ML, machine learning, it's not always all AI, but for me, I describe it as learning without explicit programming, typically to predict an outcome. So deep learning I view as a subset of ML. Deep learning typically involves neural networks. So some of you may not be familiar with neural networks. But again, all these categories of computing, ML, deep learning, they're different from my perspective, from traditional analytics in that they use a lot of non-additive math. So ML, where they're using classification, factor analysis, regressions, and whatnot. Typically, you have a high ratio of compute to data, whereas traditional database programming or processing, you have a lower ratio of compute against additive math against the data. So traditional, typical databases, you do a select, sum, average, standard dev, whatnot, group by relational algebra. All right, so AI, ML, and deep learning have different imperatives. This is basically all the algorithms out there, not all of them, but a good subset of them. Sometimes they seem daunting, all of them. How would you leverage all this for your business? How would you use them? And again, it's pretty daunting, but fortunately, there are libraries, especially Python, that pretty much has if it's not the superset, it comes close to being the superset of all the ML AI libraries out there. So in the context of what we're going to talk about, that's significant. It's not only Python. You also have libraries in C, Java, whatnot. But again, ideally, you want a platform that leverages GPUs, hopefully in-memory computing, to get the highest performance throughput and simplicity of your actual architecture and infrastructure. Okay, so machine learning, AI, whatnot, is more popular than ever. We're here at this conference. It's a central theme. We're talking about it. Personally, I believe that there's a confluence of factors, but we've delineated why. More data, more RAM, and the fact that we have GPU, we can operate against the big data and glean these insights. And these, by the way, I consider sort of the hierarchy. AI encompasses machine learning. Machine learning encompasses deep learning. With that, there's an AI life cycle. Typically, and again, some of this may be old hat for some of you, but typically, if you want to deploy a smart business application and utilize AI, you have to capture data, whether that's streaming, whether that's getting flat file feeds, but you have to provision for that. You have to train, you have to identify your algorithms, train typically on the data, and then deploy the products of that training to applications that use that to predict something. So again, you might run classification, price groups, demand groups. If you're a retailer, what do you sell? What are your classified price groups, demand groups? You might want to forecast and run some regressions on what's the future supply and demand within those groups. So again, practically speaking, we come back to what's always been characteristic of building systems in general. It could be, again, AI, but you ultimately have to capture data. You have to apply machine learning. And one key thing that I've noticed in all the machine learning, AI-driven projects I've been involved in, 70 to 80% of the time is preparing, massaging, manipulating that data. So I mentioned Python earlier. Python will typically, use data frames, use NumPy or whatnot. But in order to construct the data frame, there's significant time, preparation of the data. And again, typically that's done relationally. So you want to use your joins, unions, group bys, preferably in a massively parallel processing paradigm, maybe shared nothing. That there's model pre-processing and post-processing that's characteristic of that. So I've seen infrastructures where that model pre-processing, post-processing can take days to hours, where we'll discuss why, but if you go to pre-processing, post-processing in an in-memory database, you could get seconds to minutes. Okay. Most typical AI infrastructures right now, they're wide. They use many tools, a deep stack, NoSQL and SQL components. I listed some of them out. So I've seen, for example, distributed compute nodes, distributed CPU, distributed GPU farms. They're separate from the storage nodes. Storage might be on a distributed file system. I also delineate that from storage systems like HBase, a custom key value store, or even another database. So orchestration of your infrastructure, running models, pipelines, model pipelines, when it involves these many components, it often requires a lot of engineering, a lot of manpower, and there are latencies. They have to be stitched together. Interesting enough, when you have delineated components like that, a deep stack, it invokes the old data shipping versus function shipping issues. So in the past, you might have some technologies where they're outside of the data stores, and again, they're moving data. Movement costs. When you're talking big data, you could, really big data, hundreds of billions of rows, hundreds of billions, even to trillions of items. If you're in a client-server mode, if you're in some execute, CPU or GPU execute node, compute node, moving that data is going to be costly. And again, all these components here, as we'll show later in some practical examples, real-life use cases that we've been involved in, Kinetica, that latency really comes to bear. And it's a ceiling on what kind of applications you can materialize. When, again, you need high throughput, low latency, combined with model processing, quickly turning that around to provision for post-processing analytics and stream ingesting, bombing the platform at the same time. Okay. And again, our aim at Kinetica, we took all those imperatives from, and all those capabilities enabled by bigger RAM, being able to be in memory, incorporating CPU, GPU, into a simpler stack. So our thesis and our experience in the field for high payoff applications, the fast throughput, has been we can do more with less. What that means is, again, we're optimized, built from the ground up to leverage CPUs, both for database processing, our query plans, our compilers. When they create an operator graph, they know when to send it to GPU, when to keep it in CPU. And again, we can withstand, unlike traditional databases, bombing it with Kafka, Storm, Flume, and with no significant degradation in terms of supporting the analytics and still running the machine model pipelines, machine learning AI model pipelines. So one thing I want to point out again is we're going to focus on Python because it's popular, right? A lot of people write Python to do their machine learning. Again, typically, when I come to a client, they have teams of data scientists we work with. Most of this Python is single-threaded. Again, they're doing ETL. They're doing relational processing in there. So more often than not, I can gut that code, and I work with the scientists, and we take out all the pre-processing, post-processing, put it in SQL. That way you can leverage also your DBAs, delineate what the DBAs do, what software engineers do, and what data scientists do. Data scientists should focus on getting their data frames, immediately recognizing the data for what it is, not having to worry about how to transform it, change it, aggregate it, segregate it. And so that was our approach. Rewrite Python code, whether it's calling TensorFlow, whether it's just NumPy or whatnot, even your own procedural code in Python. So it's amazing how many procedural programs I find also that aren't using the built-in machine learning libraries, and that's fine. Our paradigm is to write user-defined functions and run them inside a database engine optimized, again, with GPU, CPU. Okay, use case examples I want to go through. So this is all in the context of my experiences, our Kinetica experiences at a major retailer. We want to focus, these are all projects we did, last mile, fleet management. The ones I really want to focus on, though, are membership renewal, a recommendation engine, and a replenishment. So we were able to handle the intersection of these use cases, again, on one platform. So supply chain replenishment, that's when we were ingesting massively Kafka storm streams based on Kafka. We needed to support hundreds to thousands of queries a second on a 100 billion plus row table that, again, is being constantly updated. We had to support a full data science model pipeline for membership renewals, as well as a recommendation engine to recommend when you have a basket of goods, automatically be prompted if you have an app, with what other product might you buy, given your market basket. So the reason we had the opportunity was, again, alluding to earlier slide, they had a traditional, I don't know how traditional, because NoSQL is just emerging, but they had the following components. They had, your MapReduce, Spark, Cassandra. You have your distributed file systems, compute nodes, and the compute nodes themselves are delineated again between CPU, GPU. So orchestrating these processes was difficult. At least the use cases we've shown, they weren't achievable with this stack that you're seeing. And again, it's a wide stack, a lot of components. If you sum up the compute power, you would think they should match us. But again, what I want to emphasize is because you don't co-locate the actual memory, the GPU, CPU, and distribute the data accordingly, you won't get the same throughput to meet the SLAs they wanted. And because they're using heterogeneous components, also certain components here, they are suitable to, for example, create a summary table off 100 billion rows to do in an attempt to support high throughput queries, right? So we proved better at that, and we'll go through that. But there was an opportunity, again, because the use cases that we're going to go into weren't achievable with this stack because of the latencies involved. So basically, the first use case was membership renewal. So again, it's a retailer. It's some kind of club membership. People's membership, when it would expire, would get prompted every time they visited a store or they showed up online. It turned out to be a nuisance factor. So people were not renewing their membership, and that's in a low-margin retail business. Food, groceries, goods, that was costly to them. So their data scientists came up with a homegrown Python non-parametric model that, again, needed to ingest data and process the data, and every day within a tight batch window, they did this batch. They didn't do this streaming. Process the data last minute within an SLA of 45 minutes or less. So we solved, again, conceptually, this is how we deployed our solution. We had 10 nodes. We had fact and dimension tables for this prompts membership function. We also supported not only these model pipelines, specifically the prompts project, but we were still supporting those other projects, Replenishment, Backbone. And again, while all this is processing, we're bombing it with massive stream ingestion from horizontally scaled Tomcat servers that have endpoints that are supporting a machine-driven architecture, that machine-driven microservices architecture that's doing 600 to 1,200 queries a second, orthogonal to the model pipeline for the membership renewal. So every night we would run the membership renewal and generate which member should be prompted. The data science in the user-defined function Python program that we deployed computed and forecasted the frequency of visits of a member and then would stagger out the prompts. We also incorporated feedback, because in any machine learning AI, you typically want to incorporate feedback. Did the person, when he was actually prompted, did he actually respond or not? And we took that and would incorporate that into the next run. So that was the basic use case, parallel to doing these other use cases as well. Again, this is just a little bit more of an expose of what we wound up doing. We took the user-defined function. We gutted processing from it. We took processing out that was more appropriate to do in SQL. And I had good experience with the data scientists that I worked with because they embraced this approach. When they saw that certain processing was more appropriate in SQL, I mean, SQL's not that hard to master, so they wrote a lot of the SQL themselves and made it easier for the model itself to get the data more cleanly. Instead of ingesting multiple data sources, SQL could pre-process the data and give a total of 3 tables, and I'll explain why it's 3 rather than dozens, complicating the Python program. So again, this is basically conceptually what we had to do. We had, for this membership renewal, we have base tables that we had to load into, and this is your standard ETL pipelining infrastructure. You had to insert into base tables. The base tables then became the basis of model pre-processing. We would run the model pre-processing, and then we would create intermediate model structures. All that means is just a fancy way of saying we created a small amount of tables that would be input into the base model table. And so the model processing itself, again, Python, you'd input 3 tables, basically. A main model table that was a record of visits, feedback, taking into account feedback, as well as 2 tables that were, for essential purposes, classification tables, what clusters a user belongs into. So 3 tables were ingested. We started, there were 2 processes that were written in Bash to orchestrate all this. FTP would drop files, we'd load them. The second process would kick off sometime after the first, get the most updated data. We again load that and then commence with the said model pre-processing. That model pre-processing was taking hours using a Spark HiveQL and Teradata stack. Okay, and again, we were able to do it because we're an in-memory database, the model pre-processing with SQL, in less than 10 seconds. Okay, so we're in memory. We're in memory, we're using GPU for also our SQL operations and leveraging the high-density cores appropriately, let alone then when we run the model, we run a user-defined function, we run a Python program to consume 3 tables that were prepared for the model. The model runs, the model then writes its output to another table. Then that table is sent to downstream systems at stores that if a member shows up, he gets prompted. And again, intelligent prompts, not willy-nilly every day that the person walks in. And so this has been in production for, I think, 2-3 months, and they're already, compared to the old way, showing a greater retention. So it took us 6 weeks to build this. I want to talk a little about now how, more concretely, how we implemented this. So basically, the model itself would take sets of members. Right, so practically speaking, there was a record. There were records associated with each member. How many times their visit history. That's all that was. So we sharded by member. That way, you get distributed processing. Any members' rows would wind up on the same node, sharding across an MPP distributed computing platform. That's just smart DBAing. You design your table. You say partition by some subset of keys, so that the superset of all rows belonging to an ID, a model ID, a member, are all co-located. We replicated the small classification tables on each node. So all computing was local. We didn't have to do any data shipping, redistribution, resharding, reshuffling. And I've had these experiences. I've tried with their team on Spark, with RDDs in memory, co-locating, and there was still a lot of shuffling going on. So even when we replicated tables in HiveQL, I remember the smaller dimension tables, you still had significant reshuffling. It was non-deterministic. But again, that in comparison, the HiveQL to do all this was taking hours versus us doing it in seconds. Okay. Now, once the Python fires, we're not going to be any faster, admittedly, than if you ran it on your own GPU farm. But again, when you factor in that the data processing, pre-processing, post-processing, we can generally sustain higher throughput, meet SLAs, especially, again, if we take out critical processing that doesn't belong in the actual model process. But strictly speaking, the model itself, you run a regression of whatnot, inverting matrices and whatnot, GPU is GPU. Again, we have a platform, however, that uses the GPUs and CPU, by the way, appropriately for database processing as well as the model processing. You can also set these up, orchestrate them, so you can divide what GPUs the models run on and not taking all of that to block the database, and it can have its own complement of GPU. Okay, this is just a recapitulation again of a previous slide, but what we did is we went from the paradigm on the left to the paradigm on the right. And again, DBAs, the scientists themselves, were smoothly able to do this. They were able to take their Python and separate out what should be in SQL, what shouldn't. They're all smart people. They understand the difference between additive, relational, algebraic processing versus non-additive math involved in ML and deep learning. So this basically illustrates our shared nothing distribution strategy. Base tables that we created, those member tables. Remember I said we're sharding them by member number. So any members' visits are always on one node and only one node. We sort them before we actually call the model itself and use 2 replicated tables. So 3 tables are input. Very clean, very easy. That pre-processing also, the input rows on the main member table. Remember, it's already pre-processed by SQL, so we greatly reduce the data set. Instead of billions of rows, we reduce it to only those members that stand a good chance of being prompted. We filter a good number of them out. Previously, they were running every member every time. And again, this is all in memory. All the data is in memory. You don't have to read HDFS. You don't have to read some other data source database, use JDBC, ODBC to a compute farm. And typically, again, when I see different compute farms, they're delineated. They first come to a CPU, maybe a Java process runs, a Python process. They get all the data, do the aggregation, filtering, whatnot there, and then they have to ship it off to a GPU farm. And that eats up time. That definitely impacts your throughput. Sorry, the microphone isn't cooperating with me. So again, this is just a summary of what we did. So the summary of the solution was we use sharding, we use replication appropriately, shard the main data, if you will, the fact table. In this case, the fact table was the primary model input, the classifications for members, what clusters they go in. Those are 2 small tables, each with about 100 rows. They're replicated on every shard. And again, this facilitated what I was talking, and by the way, it incorporated feedback as well. That whole orchestration where we ingest data. So I want to emphasize any good machine learning model, a little bit orthogonal to provisioning for it, but it should include feedback. You want a whole pipeline where it incorporates extraneous events based on what you're forecasting and predicting, and incorporating that again into the model. So this facilitates fast batch ingest, fast analytics, and everything pretty much what we summed up earlier. So I want to talk about this because remember I said, in addition to hosting this model pipeline, we also were hosting a replenishment, or inventory replenishment application. So this one is interesting too because this one I was able to also measure what the competing NoSQL stack was doing in terms of a solution attempt. Here we had 100 billion plus rows. Every 5 minutes, we had to create a 1 billion row temp summary table. So this was inventory replenishment. Machines were calling a microservices architecture, and they needed to sustain 600 to 1,000 queries a second. Okay, so they couldn't do all this functionality, the retailer, with any single component of the NoSQL stack. They tried to do creating the summary table in Spark using HiveQL. It took anywhere from 1 hour to several hours to create that summary table. We create the summary table in less than 10 seconds. Again, it's in memory, it's using GPU, and then we can support 600 to 1,200 queries a second. While all this is going on, while ingestion is going on, while we were running that model pipeline. That's all, again, a homogeneous platform. The other thing is Spark wouldn't support 600 to 1,200 queries a second. So what they attempted to do is, after an hour, after several hours, ship the summary table to Cassandra. So Cassandra could definitely read 600 to 1,200 queries a second. So Cassandra's well built for that. But Cassandra can't do aggregation. Cassandra doesn't do joining. It doesn't have the range of relational operations. So if you give Cassandra 100 billion rows and you wanted to create the summary tables, the SQL involved in that wasn't achievable by Cassandra. So we were able to do all that, right? We were able to facilitate this concrete example of how a modeling pipeline wasn't meeting the SLAs. Again, the previous modeling pipeline, the prompts renewal, you could achieve it in Spark Cassandra. That one you could, but you couldn't meet the SLAs. And this one you just couldn't achieve at all with the NoSQL stack. This slide here just illustrates the main differences, differentiators we think we have relative to these other components. Spark, and you could kind of put Spark, Cassandra, MapReduce together, but I think we're appropriate. An engine like Kinetica, again, for high payoff applications and analytics where you need extreme throughput, extreme ingestion, coupled with model processing using AI, machine learning. Again, traditional SQL databases, they don't do a very good job of ingesting data. If you try to use one of the major SQL vendors and hit it with Kafka Storm, they're going to have their issues. And completing those transactions as well as executing queries live. Again, Spark can do a good job ingesting, not as good a job supplying high throughput querying, analytic querying, especially across large data sets through HiveQL or whatnot. The other thing I want to bring up is, so Kinetica is engineered from the ground up. It's written in C. So I'll answer questions later, but if you're aware of what NUMA-aware programming is, so when you write in C, unlike Java, I can schedule a thread on a core. When that thread leaves some data behind or data structure, I can schedule the second thread that's going to pick it up. On the same core, it'll find it in L1 cache. I mean, Java has no concept of that. It would be coincidental in Java. And that adds up. If you're hitting L1 cache in CPU consistently across big data, billions and billions, it really makes an impact. You're talking order of magnitude to several order of magnitude, especially when you're doing set-oriented SQL. In addition to that, again, Kinetica also has the density of the GPU card. So when appropriate, we push even database operations down to that GPU. So we leverage NUMA when we stay in CPU. When we stay in CPU, because we're highly vectorized, We also use SIMD and AVX, which to my knowledge you can't do in Java. And again, the classic NoSQL stack, they're all coded in most of them, at least, the ones I mentioned, Spark, Cassandra, Java. Again, that's my presentation. Thank you for your time. I'd love to open it up for questions.